Okay, in this video we are going to take a look at simplifying radical expressions. Before we start on that topic, just a quick review of some terminology. This is probably just a refresher for most of you. When we talk about radical expressions, we're talking about something that could look like this. There's a radical expression. There's another one. And right away we notice these both have that check mark symbol. That's what we call our radical. I'm sure you guys have heard this terminology before. Then we have the number or expression that's underneath the radical. That value is called the radicand. And then finally, we have the little number that's out front. It's kind of like a superscript, or sometimes it is missing. That value is called the index. In the first example, our index is 3. In our second example here, it looks like the index is missing, but again, you probably know that anytime there's no number out there, it's assumed to be a square root. So that means our index is 2. And so here's kind of a basic outline of our procedure. The first thing we're going to do is find the prime factorization of the radicand. And if you don't know what prime factorization is, that's okay. We're going to go over that. But we'll find the prime factorization of that number underneath the radical symbol. We will figure out what our index is, and then we will use those two pieces of information, number 1 and number 2, to figure out what kind of simplifying can be done. And that means what can be pulled outside of the radical symbol. And then we will clean up our final answer and keep in mind that simplifying here at the very end means multiplying. Okay, so here's the first few examples to look at. First of all, the prime factorization of that radicand. The radicand is 12. And when we want to write the prime factorization, we start off by splitting our value into any two factors we can think of. There's no right or wrong answer here as long as you have two factors that evenly go into 12. For example, we could start with 3 times 4. Okay. 3 is a prime number, so it's done. We don't do anything else with that branch, but 4 is not prime. 4 can be split again into 2 times 2. 2 and 2 are both prime, so those branches are done. So what we've found out here is that 12 is the same as 3 times 2 times 2. Okay, that's one piece of our puzzle. Next up, what is the index for this specific problem? Again, that's going to be the easiest thing to determine. The index in this case is equal to 2. Because there is no index, we know it's a square root. And that index tells us how many pairs of values need to be present underneath the radical symbol before they can come out of the radical symbol. Okay, how many copies of a factor do we need to see in order to pull it outside of the radical? So in this example, we've got the square root of 12, which we just said is the same as the square root of 3 times 2 times 2. Our index is 2, so we are looking for pairs of numbers. And we can see right away here, we have a pair of 2's. Okay, a pair of 2's means that 1 2 can come outside of the radical symbol when we simplify. So this simplified is going to be equal to 2 times the square root of 3. 3 has to stay inside because there was no partner, there was no pair of 3's, but the 2 got to come out because there was one pair. Okay, let's do some more of these. So again, we start off with that radicand. We start off with 24, and we want to write the prime factorization. Pick any two factors. You could pick 2 and 12, or 3 and 8, or 6 and 4. It doesn't matter because we'll work our way down either way. Let's just start with 6 times 4. 6 is not a prime number. It can be split again into 2 times 3. But those are both prime, so we're done there. 4 is not a prime number. It can be split again into 2 times 2. And there we have it. Our prime factorization for 24 is 2 times 3 times 2 times 2. Okay, for this one, our index this time changes. Our index is not 2 anymore. This time our index is 3. That means we need 3 copies of a factor before it can come out of the radical symbol. Okay, so we notice right here we have 1, 2, 3 copies of the number 2. That means one set of 3 means 1 2 gets to come outside. That 3 has to stay inside, and make sure you keep the index the same. It was a cube root to begin with, so our simplification is still a cube root. similar to our last answer. Okay, here's another one. The square root of 1,575. And that might seem a little intimidating at first to have a big number like this, 1575. And I don't happen to have memorized the factors of this value. It's too big. But we notice right away that it ends in a 5. So this number must be divisible by 5. And at that point, just grab your calculator if you need to and do a division. Figure out 5 times 315 gives me 1575. So the 5 is prime. We're done on that branch. But 315 is not. It is also divisible by 5. So again, grab your calculator if you need it. Turns out that 5 times 63 gives me 315. 63, now these are factors I know again. 63 is 9 times 7. 7 is prime, so that one's done. 9 is 3 times 3. And there's my prime factorization. For this one, again, no index, so that means that it is 2. It's a square root. That means we're looking for pairs of values. Here's a pair of 5s, so 5 gets to come outside of the radical. Here's a pair of 3s, so 3 gets to come outside of the radical. 7 is all by itself, so 7 has to stay inside the radical. And then this is where we have to take that final step 4. We didn't have to do this in the last two problems, but we want to simplify this. Those two numbers that get pulled outside of the radical, they get multiplied together. So our final answer is 15 times the square root of 7. Okay, another one. I just want to go through as many examples here with you as possible so you can see how these work. This time, our radicand is 432. Again, if you're not sure of the factors of that value, grab your calculator. Since it's an even number, we know it's divisible by 2. And it turns out that it's 2 times 216. 216, we can split again. That's 2 times 108. 108 can split again. That's 2 times 54. 54 can split into 2 times 27. 27 is 9 times 3, and 9 is 3 times 3. Okay, it's kind of long, but you just chip away at it until you get the information that you need. And our index this time is 4. So that means we are looking at groups of 4. Anything that comes out of the radical has to, oops, sorry about that, has to appear, let me bring that back up. Anything that wants to come out of the radical has to appear 4 times. So here we go. Here's 1, 2, 3, 4 2s. So a 2 gets to come out front. We've got 1, 2, 3 3s. So that has to stay inside. The 3 can't come out. So 3 times 3 times 3 stays inside the radical. And again, we want to simplify for our last step. 3 times 3 times 3 is 27. So there is our simplified radical for that 4th root. Okay, another big number. Again, this might look a little scary at first, but you just have to chip away at that. This time we have 5,832. Prime factorization, again, it's even, so I know it's divisible by 2. And just grab your calculator. It's 2 times 2916. Again, even, 2 times 1458. And we get 2 times 729. And this one is not even, so 2 is not going to work anymore. I'm going to try 3. And when I divide that out on my calculator, it comes out. It's 3 times 243. And 243 is also divisible by 3. 3 times 81. There's one that I recognize. 81 is 9 times 9, which is 3, and a 3, and a 3, and a 3. Okay, so there's our big prime factorization. This time again, our index is 2 because it's a square root. So we are looking for pairs of numbers that can come out. Right here, 1, 2. There's a pair of 2s. And there's 1, 2 that's going to be outside of our radical. There's a pair of 3s right there, so that's 1, 3 that can come out. But we've got another pair of 3's, 1, 2, so another 3 comes out, and another pair of 3's, so that 3 comes out. What's left inside is just this little 2 right here. Again, simplify those. 2 times 3 times 3 times 3 is 54. Sorry, that's a little sloppy. 54 times the square root of 2 is our simplified answer. Okay, so in these examples so far, we've only had values, constants. We want to throw some variables in the mix. Procedure is really very similar. We don't necessarily call it the prime factorization, but we're doing the same kind of thing. Here, let me change my color. X squared is the same as x times x. So I'm going to write it like that. Our index is 2. That means we are looking for pairs of factors to pull out. Right here we have a pair of x's. One pair means one x comes out of the radical. And there's our simplification. Again, you probably knew that one without doing the work, but I wanted to start with the basics. Same kind of thing here. X cubed is x times x times x. It is still a square root, so we are still looking for pairs. Here's one pair of x's, so one x gets to come out. That other x has to stay inside. And same idea for x to the 4th. Still a square root, so we're looking for pairs. There's one pair. Here's another pair. And we're not left with anything inside the radical, but we can simplify that. X times x is the same as x squared. Now, obviously, when you got to higher powers of x, I don't really want to take the time to write out x times x times x 15 times to circle all my pairs. But another way you can think of it, we just need to ask ourselves, how many pairs are in 15? Okay, or another way to think about that is 15 divided by 2. 7 pairs inside 15, but it's not even. We have a remainder. So your answer, that 7, tells you what comes out of the radical. Excuse me. And your remainder tells you how many have to stay inside the radical. So this answer is going to be x to the 7th, because 2 went into 15 7 times, times the square root of x to the 1st. Usually if it's the 1st, we don't write that exponent because there was a remainder of 1. So that's kind of some of you might be able to do this intuitively, but if you need to write it out, that's kind of a quick and easy way to do it. Okay, this time we have the cube root of x to the 32nd. So we want to know how many groups of 3 are there in 32. So again, we can just do a quick little division here. 10 groups of 3 and 2 left over means that we have x to the 10th on the outside, and x squared has to stay in. Don't forget the index stays the same when we simplify. And we can have problems that have both numbers and variables in them. Due to the properties of exponents and radicals, what you can really do is just break this up into 2 separate problems if you like, because we know how to do each one of these now. The square root of 8. 8 is 2 times 4. 4 is 2 times 2. So there's our prime factorization. Since it's a square root, we are looking for pairs. So there's one pair. 1, 2 comes out. 1, 2 stays inside. Then over here, we actually already did this in one of our previous examples. X cubed is 1x gets to come out. 1x has to stay inside. These pieces are all factors. They are all multiplied together, so we can now combine this. Anything outside of the radical can be combined. 2x. Anything under the radical can also be combined. There's our simplified answer. And another combination one here, same kind of idea. We've got the cube root of 81 and the cube root of x to the 5th y squared. 81 is 9 times 9, which is 3 times 3 times 3 times 3. Cube root this time, so we are looking for groups of 3. We have one set of 3 factors, so 1 3 gets to come out. There's a 3 left inside, so we'll leave that one behind. And then over here with our variables, again, cube root, so we're looking for groups of 3. With our x, we have 5 x's. So that means there is one that can come out that represents 3 x's inside the radical, and that means we are still left with 2 more inside because we took out one group of 3. Oh, sorry, that should be an x squared, not a y squared. So that took care of our x. Our y, 2, we have y squared. There is not a group of 3, so the y has to stay inside. Okay, so now we'll put these two pieces together. Sorry, we got a little messy there. We have a 3 and an x on the outside of the radical. Then inside we have 3 x squared, y squared. Okay, there are an unlimited number of examples I could go over, but that hopefully gives you some basic skills that can help you with types of problems where you need to simplify the radical. The last thing we need to look at, I just wanted to mention this, make sure you notice, we can simplify factors, but we cannot simplify terms. Again, properties of radicals and exponents. For example, this problem right here does not, no way, never simplifies into x plus y. Okay, you cannot take a radical and split it into x squared plus y squared like this. So let's put a big no on top of this because we don't want to do that. Okay, if you were given this problem and asked to simplify it, there's actually nothing you can do. There's none, no simplification. Okay, that is as simplified as that one gets. Okay. Notice this problem's a little bit different. Okay, instead of x squared plus y squared, we have the quantity squared. The whole expression is squared. So this, if we wanted to, we could write it as x plus y times x plus y. Notice we have 2 copies of this factor. These things are multiplied together. So that means that this would simplify into just the expression x plus y. Okay, so I just want to make sure you notice the difference between, you got to be careful with your factors and your terms.